Farewell to Kentucky, we're live. Gas stoichiometry. All roads lead to mole. So, given information about pressure and volume, you can get to moles using gas laws. Hello, kitty cat. Off the desk. Gotta be able to see. All right, so this just means that there's another way for us to set up a reaction and ask you to come up with regular Stoic problems. Okay? Nothing particularly new here. We're just reconnecting this new information, these gas laws, with older stuff. Careful, that lamp bulb's hot. All right. So gas Stoic means we just have another way of getting in and out of this. So how many liters of CO2 are produced by... There's not really enough room for you there, kitty. All right. Produced by decomposing 5 grams of calcium carbonate at STP. So remember, standard temperature and pressure. Temperature is going to be 298, and pressure is going to be 1 atmosphere. So we are decomposing 5 grams of calcium carbonate. Ow. All right. So we're going to need the molar mass of calcium carbonate. So we're also going to need a periodic table because I don't remember the molar mass of calcium. So calcium 40.078. And now I can bring the calculator back up. So 40.078 plus 12.011 plus 15.999 times 3. 100.086 grams per mole. 5 gives us 0.04996 moles of calcium carbonate. Now, we're also going to need a balanced reaction. Fortunately, that's really easy in this case because when you decompose calcium carbonate to make calcium oxide and CO2, it's 1 to 1 to 1 to 1. So, no trouble there. So this is just going to be 0.04996 moles of CO2. And now, that is what we can plug into PVnert. So volume equals nRT over P. 0.04996 moles times 0.08206 liter atmospheres per mole Kelvin times 298 Kelvin, 25 degrees Celsius, divided by 1 atmosphere of pressure. 0.04996 times 0.08206 times 498. No, not 498. 298 means that it's going to be 1.222 liters of carbon dioxide. Okay. So that is one way to make CO2, is just to heat up limestone and break out the CO2. It's not something you necessarily want to do, but yeah, maybe for industrial purposes. Who knows? All right. A mixture of 5 grams of hydrogen and 50 grams of nitrogen are reacted to form NH3 in a 50-liter container at 600 Kelvin. What is the pressure inside the container when the reaction is complete? Assume a 100% yield. So this is a limiting reactant problem. All right. So once again, we'll need a balanced chemical reaction. This is what is not going to be 1 to 1 because N2 plus H2 yields H3. We're going to need 2 of these and 3 of these. So we have 50 grams of N2. We have 5 grams of H2. Convert them both to moles. $50 divided by 28.014 gives us 1.7848 Yep. Moles of nitrogen, 5 divided by 2.0158, gives us 2.480 moles of hydrogen. And now, of course, it's not enough to convert them to moles. We have to compare them in the context of the balanced reaction. So we divide by 1, we divide by 3. 0.8268 means that this one is the limiting reactant. Okay, we're going to have nitrogen left over. And that is important, okay? Because in addition to having gaseous ammonia inside this container, we will also have nitrogen inside the container contributing to the total pressure. So, 2.480 moles of hydrogen times 2 moles of ammonia divided by 3 moles of hydrogen, because we produce 2 moles of ammonia for every 3 moles of hydrogen we consume. Means we're going to produce 1.653 moles of ammonia. But, like I said, we're also going to have nitrogen left over. So 2.480 moles of hydrogen times 1 mole of nitrogen for every 3 moles of hydrogen. I already calculated that. 8268 moles of N2 used. Okay, so we're using up some of our nitrogen, but not all of it. So how much are we going to have left over? That's going to be 1.7848 moles minus the 0.8268 that we use. Okay. We're going to have 0.9580 moles left over. Okay. So the total number of moles is going to be this guy here plus this guy here, because we have both nitrogen and ammonia inside of our container. So our total N is, those two added together, 1.653 plus 0.9580, 2.611 total moles. So our pressure is nRT over V, 2.611 moles times 0.08206 liter atmospheres per mole Kelvin times what temperature? 600 Kelvin. And then what volume? Can't read it. 50 liters. So 2.611 times 0.08206 times 600 divided by 50. The pressure inside that thing is going to be 2.571 atmospheres. So be aware that when you have a reaction happening, you might have some of your product left over. So limiting reactant problems can be tricky like that. Okay. So let us continue talking about gas stoichiometry. Actually, that might be the end. It is. Okay, so gas stoichiometry doesn't really add anything new, except it's just another way to move back and forth per moles. It's another quantity they can ask you about. Instead of asking you how many moles or how many grams or what molarity, they can ask you about the pressure or volume of a gas. Okay, and with that, we are done with gas stoichiometry. And just to make it easy on myself, we're going to go ahead and call it a night. I will finish these next 2 sets of slides tomorrow evening, because I can.